we're going to start the last chapter, radioactivity, and which is not a difficult one. Perhaps it's the easiest in this level. So let us start with the major aspects of radioactivity and what we need to know. And of course, this is the structure of the atom. We have seen it many times before, where we have the nucleus at the center of the atom, consisting of protons and neutrons. Both together are called nucleons because they make up the nucleus. And the nucleus is surrounded, of course, by the electrons, which are found in orbitals. But considering that we're talking now about radioactivity, we start the topic of radioactivity and nuclear physics. The electrons are not so important in this field. We ignore them and we concentrate on the nucleus, in the nucleus especially. So basically, how do we represent a nuclide? With this symbol, where X is the chemical symbol of the element that the nuclide represents. Z is the atomic number, which is actually the number of protons in the nucleus. And A is the number of nucleons altogether, protons and neutrons, and that is why it's called the mass number, because really this represents the mass, the relative atomic mass of the nuclide. And okay, so this is the basic representation, which we have seen many times before, which is how we represent actually isotopes of an element. Which brings us now to the topic of isotopes, where isotopes are, like here some examples, with the hydrogen and the carbon. These three are the known isotopes of hydrogen. The top one with just one proton in the nucleus is called also the protium. Another isotope is one that consists of a proton and a neutron, and we call it deuterium. And the third isotope consists of a proton and two neutrons, and we call it the tritium. Deuterium is the isotope of hydrogen that we find in heavy water that is used in reactors, nuclear reactors, and so on, to moderate the reaction. But protium is the most common isotope in nature, the most common hydrogen that we find in nature. And here we have, again, some examples of isotopes of carbon to remind us what we need to remember is, when it comes to isotopes, is that isotopes are the same element, belong to the same element. They have the same number of protons, same atomic number, and neutral atoms, of course, the same type of neutrons. It's just the number of what did I say? The same number of electrons in a neutral atom. The only difference between isotopes of the same element is the number of neutrons in the nucleus. So isotopes are nuclei of the same element with different number of neutrons. Just to remind ourselves, just in case we forgot. And each one of these items here is called a nuclide. So a nuclide is a nucleus actually with a specific number of protons and neutrons. And why the necessity of calling them nuclides? Because you see, in chemistry, all these isotopes are the same element and have same physical and chemical properties. But in nuclear physics and the nuclear processes, each one of these is a very different species. So that is why we need to distinguish, and each one of them, we call them a nuclide without having to refer to the isotopes of the particular element. So a nuclide is a particular nucleus that has so many protons and so many neutrons, and we don't have to call it isotope. All right. Very quickly now. Now, since we are talking about nuclides, it's good to know that from now on, when we represent nuclides, there's no need to include the atomic number at the bottom the symbol of the nuclide. Why? Because, say for nitrogen, a nitrogen can only have 7 protons. And therefore, when we know that this item here has 7 protons, it's definitely nitrogen. And also, if we know the chemical symbol, we know that this has 7 protons in its nucleus. And if we know that some item has 7 protons, it's definitely nitrogen and nothing else. So from now on, if we know the chemical symbol of the nuclide, we can omit the subscript Z. The subscript Z is the atomic number, the bottom number. We can rewrite the examples above, these examples, as simply hydrogen 1 or carbon 15 or nitrogen 15, gold 198 or uranium 238. There is no need to include the Z here, this number Z. Okay, so from now on, we are going to call these nuclides as, for example, this one, for example, will be uranium 238. There's no need to say anything else, and we know what it is. Now, from now on, let us start with something new now that perhaps you have not seen before in previous levels. It's about the nuclear stability. Yes, we have, in IG level, yes, we have spoken about radioactive decay and so on, but now we're going to discuss this a little bit more in depth. And what is this story about the nuclear stability? The story originates in the fact that in the nucleus consists of protons and neutrons, okay? Protons have a positive charge, but neutrons are neutral. So one might question, and very reasonably, how is it possible that the nucleus stay together since the protons should repel one another through the electric force, isn't it? Because like charges repel. How is it possible for that the nucleus stays in one piece? And it's a very justifiable comment, of course, which means, so if we think of it, obviously in the nucleus there must be some other force, or at least another force in addition to the electric force that should be acting between the particles that make up the nucleus which we call the nucleons, isn't it? The nucleons. And indeed, there is another force that we meet inside the nucleus, and this is the strong nuclear force is called. We are going to discuss again about this force, but just to discuss a little bit about, to introduce the stability. So you see, the reason, so the strong nuclear force acts between nucleons, and it's always attractive. It's an attractive force. And this force, we have not met it anywhere else in our everyday life. In our everyday life, we know about the gravitational forces, the force of gravity, and we know about the electric forces, electromagnetic forces. All these forces are one type of forces. And all the other forces that we have met, like the force of friction or the normal force or any other forces like pushes and pulls that we meet in mechanics, all these are electrostatic in nature. So all the forces that we meet actually are electrostatic in nature, except for the gravitational force, which is a force on its own. And but now we meet a third type of force, which is the strong nuclear force that acts only in the nucleus, the strong nuclear force. And this is the reason why the nucleus stays together, because a strong nuclear force is much stronger than the electrostatic force, the electric forces altogether that exist between protons. And the strong nuclear force is always attractive, we said, and acts on all the nucleus. All the nucleons experience this force, both protons and neutrons. It's not an electric force, it's a very different type of force. So all nucleons experience this strong nuclear force, and this is the force that keeps the nucleus together. The problem with this force, though, is that it's a very short range force. It acts at very, very short distances. And therefore, while it acts at distances which are comparable with the size of a nucleus, but not any nucleus, but small nuclei. If we consider large nuclei, this strong nuclear force cannot reach to the other side of the nucleus, so it cannot keep a lot of stability. Nevertheless, now we come to the point of stability of the nucleus. We see now, the best way to understand this is if we look at this chart here, or graph. This graph represents, okay, it looks very unclear, but if you look at the two axes, now this horizontal axis is the number of protons. So you see, as the axis, as we move to the right-hand side, the number of protons in the nucleus increases. And the vertical axis corresponds to the number of neutrons, because remember, the nucleus is made out of protons and neutrons, okay? So this graph actually gives us an idea of the balance between the numbers of neutrons and protons in the nucleus and what happens. Now, I would like us to make it a bit bigger. If you look here, you see every little square, if you look at every little square here, corresponds actually to an isotope of an element that has a particular number of protons. Okay, so all right. So you see, if we go up, let's say at the 14, since we have a 14 here, if we go up along this line, all these little squares, which are first blue and then they become black and then they're orange and pink. All these squares along the same straight vertical line actually correspond to isotopes, are all representing isotopes of the same element that has a proton number, an atomic number 14. What is this 14, atomic number 14? If we look at our periodic table, the number 14 is, what is 14? Silicon. Number of protons, the atomic number of silicon is 14. Now, if we look now, all the black squares here in this chart, all the black squares correspond to stable isotopes. All the other colors represent unstable isotopes that decay. Now, look at this line here from the beginning. Well, it's supposed to start from 0, from 1 actually, from 1, which corresponds to hydrogen, from 1 up to about 20, about somewhere here could be about 20, isn't it? With atomic number 20. It's only up to here we see that this black line, these black isotopes, which are the stable isotopes, seem to fall on this straight line that corresponds to atoms, or rather isotopes that ought to have the same number of protons and neutrons. That means this, you see this straight black line, this means that the number of protons, the number of protons equals to the number of neutrons. Now let us zoom out again because we need all the line here. You see, only the first 20 elements fall on, I mean, the stable isotopes fall on this line that corresponds to the same number of protons and neutrons. In other words, N equals Z. Above the atomic number of 20, which is somewhere here, above that you see all the isotopes above this 20, above the atomic number of 20. Now the stability seems to lie above this line of N equals Z, which means that above this line, in order to keep stability in the nucleus, we need to have more neutrons than protons to keep the stability. Up to 20, up to the atomic number 20, stable isotopes are the ones that have equal number of protons and neutrons, remember. But above that, the number of neutrons has to increase in order to maintain some stability inside the nucleus. And that is why we see the stable nuclei now deviate from this line. And they are above this line, which means more neutrons are needed. And if you look, these black isotopes, the stable isotopes, kind of last up to there and then they disappear, which means above this line, which is 82, there are no more stable isotopes. In other words, for an atomic number, for elements with atomic number above 83, actually, above 83, which is bismuth in the periodic table. If you look in the periodic table, the bismuth has an atomic number of 83. Above bismuth, which is above all these isotopes that lie to the right-hand side of this line, of this dotted line at 82, all these now are unstable. There are no stable nuclides beyond bismuth. And that is why we see these black isotopes that represent the stable isotopes disappear. Now, all of them, in other words, are unstable and decay. At least before bismuth, there are some stable isotopes that we can find in nature. Anyway, so we see, in other words, that the neutrons kind of maintain some stability among the protons, in between the protons, because the neutrons experience the strong nuclear force, the attractive strong nuclear force, and kind of maintain some stability. But as we go from 20 up to 82, the number of neutrons have to exceed the number of protons to maintain some stability. And beyond that, there is no number of neutrons that can maintain stability in the nuclei, and they are all unstable. The large nuclei are all unstable. All right. Another interesting thing before I change this page is, look at this. You see this blue area, all these blue isotopes here that belong to this blue, above the black line, have more neutrons than necessary to maintain stability. And this decay with a beta minus decay, here they are. All these nuclides that are shown in blue decay with beta minus decay. They have more neutrons than they should. Whereas the isotopes or nuclides which are below these stable isotopes, which are shown in orange, these have less neutrons than necessary to maintain stability and decay with a beta plus decay. And we see that above the atomic number of 83, in other words, from the big nuclei, the big nuclides, mostly, you see yellow, these decay by alpha emission. I don't know if you have gone there to look at, if you have arrived in your studies, I mean, in this chapter 16, which is the last chapter of your level, if you have managed to arrive at this radioactive decays, but I mean, perhaps you remember from the previous level, the IG level, that there are 3 types of radioactive decay: alpha, beta, and gamma. And now we kind of delve in more depth into this kind of decays. But I hope you remember what the beta decays are, and what is the alpha decay, and what is the gamma decay. And if you don't remember, we're going to do it in any case. So I think this is a nice chart to give us an idea of the stability of the various nuclides out there. And the important thing to understand is that up to atomic number 20, stability is maintained if the number of protons equals the number of neutrons in the nucleus. Above atomic number 20, then we have to increase, the stability is achieved by more neutrons than protons. But I mean, not just any number of neutrons, because you see, actually, the majority of isotopes And there are many isotopes. And it's not even rare to have like 30 isotopes per element, even more than that. But the majority of isotopes are actually unstable. Very few are stable, as you can see. Very few isotopes are stable. Okay, what else can we say here about the nuclear stability? Let's read that. Above 20, stable nuclides tend to have more neutrons than protons. As we move to nuclides with higher number of protons, the electrical, in other words, higher atomic number, the electrical repulsion between protons increases and more neutrons are necessary to maintain stability by exerting only the attractive strong nuclear force. Okay, we've spoken about that. Above bismuth, which has an atomic number of 83 and beyond, no number of neutrons can maintain stability, so that is why all of these are unstable. All these are illustrated, okay. In general, if a nuclide has too many or too few neutrons relative to its protons, it is unstable. And we can see it. I mean, if we follow any line of these vertical lines, like this line 50, anything which is in the blue range and anything below in the orange range, these are all unstable because these have too few neutrons relative to the stable configuration, and these, the blue ones, have all too many neutrons relative to the stable configuration of neutrons and protons, which are represented by the black squares that correspond to the stable isotopes. Now, guys, before we move to another page, and do you understand roughly what's going on with this graph here? And let me see your messages in the meantime. It says, I don't understand the issue of squares corresponding to isotopes. N equals Z. What? Being the number of neutrons, isotopes are variants of a particular chemical element which differ in the neutron number and consequently in the nuclear number. Yeah. Okay, let's see a bigger picture here. Here is something similar. It's a part of this chart above, but magnified to see various squares more individually. You see, as we go, oh, goodness, no, I don't really like that. Let's concentrate here. I'm saying that each of these little squares, for example, like let's follow the 14, okay, because we have a line here, the 14, atomic number 14, which corresponds to silicon because it has corresponds to all the isotopes that of silicon that have 14 protons. So you see this first little square here. Can we make it bigger? Let's see how big can we make it. Let's make it 400. Let's increase. Okay, so this first little square here, you see this little square. This corresponds to an isotope that has 14 protons. And if we go horizontally, it's about, say, I don't know, six neutrons. 14 protons and 6 neutrons, okay. This corresponds to an isotope of silicon that has 14 protons and 6 neutrons, okay. If we go to the next square, the next little square, again corresponds to 14 protons, it's again silicon, but now this is another isotope that has, like, I don't know, 7, say, 7. This one will have 14 protons and 7 neutrons. It's another isotope of silicon. The square further up has 8 neutrons. The square further up has 9 neutrons, and so on. So each little square of this corresponds to a particular isotope of silicon, as long as we are all following up this vertical line that starts from the 14. Remember, this is the number of protons, okay? These are protons, number of protons. Similar with the number, this 28, this atomic number 28. If we follow this line up, we're going to meet all sorts of isotopes of the element that has an atomic number of 28. Was it 28? Yeah. What is 28? If we look in the periodic table, it's nickel. So all these squares correspond to isotopes of nickel with various number of neutrons in the nucleus. The number of neutrons is given by this number that we meet on the vertical axis. I don't know if it makes sense now. So you see these represent various isotopes that we find in nature, or we can manufacture, synthesize in a lab artificially. And of course the squares, which are like black, like these ones, correspond to stable isotopes that do not decay. Does it make sense? Yes, it does make sense. Yeah, good. I also see the other previous comment there that says, is it only hydrogen and carbon that have isotopes? No, all the elements have isotopes, and many isotopes. All elements have isotopes. These are just two examples, because the hydrogen is such a common element, and also carbon is such an important element in life and for living organisms. And we use a carbon-14, actually, this radioisotope, to date old objects, isn't it? They are important kind of elements. That is why I chose examples of hydrogen and carbon. But all elements have isotopes, and not just 2 or 3, they have millions. They have many. Okay, we said even 30 isotopes, even more than 30 isotopes, is not uncommon. There are many isotopes, and remember, we can also synthesize isotopes artificially, even if these isotopes do not exist naturally. But the truth is that most of these isotopes are so rare, like a couple of atoms, perhaps, sometimes a couple of in nature. Some of them are really very, very rare, and the relative atomic mass of the elements actually made out of 2 or 3, the most common ones in nature. Okay. So why many books use carbon-14 isotope? Because the carbon-14 isotope is a very important isotope. This is a radioactive isotope. It decays. The carbon-12 is the most common carbon in nature, and this is stable and does not decay. But the carbon-14 is radioactive, and we all have it in the same ratio in our bodies. All living things have carbon-14. A very small proportion, but nevertheless, the proportion between carbon-12 and carbon-14 stays constant, and while we live, this ratio stays constant. But from the moment that we die, because we don't take up any more carbon from our surroundings, the ratio starts changing, and because the carbon-14 decays. And by measuring the radioactivity of the sample in terms of carbon-12, we can figure out how old this sample is. Anyway, perhaps we can speak sometime about how we measure the half-life, the age of various items. But carbon-14 is a very important element, isotope, precisely because we use it in radioactive dating. It's one important technique to figure out the age of objects that contain carbon. Okay, so perhaps in next week, it seems to me from your comments that it is the first time that you see this chapter, so we might go through it as well. So next week, then I suggest that we continue with a little bit of theory, like how things decay, and also the structure of protons and neutrons in the nucleus, the various types of particles that make up these major particles of the atom. And after that, we can do some questions from past exam papers. You're talking about the carbon 14. Yeah, I hope it makes sense now. Maybe in one of our examples in the future, we can talk about the decay of carbon 14, which decayed by beta emission. Well, obviously, carbon 14 is one of the light elements here. Where is carbon 14? It's in this area. So the most, so as we can see, if we have an unstable isotope of carbon 14, an unstable carbon, what am I saying? An unstable isotope of carbon, which is the carbon 14, this will decay by beta emission because it's up there in the blue area. But we're going to, we can use this example when we talk about radioactive decay, okay? And so next week we can continue again. All right, at least now I know what you know and where we stand, so we can arrange our lesson. Okay, guys? All right, guys, so enjoy your week. Have a great week and continue.